Hello guys, welcome to homework number 20B. I'm going to go ahead now and share the homework slides. So this is the first problem we have here, focus on concept question 08. It says for the circuit shown in the drawing, what is the voltage V1 across resistance R1? So these are circuit in series with the resistors in series. So we have the same current flowing through 1 and 2, which is the total current coming from here. So I1 equals I2 equals total current. So we're going to write this in terms of Ohm's law. So I1 is V1 over R1, I2 is V2 over R2, I total is V total over R total. So this statement is the same as this statement. So, but I want V1, so I'll just say V1 over R1 is V total over R total. But R total in series is R1 plus R2 right there. So V1 over R1 is V total over R1 plus R2. So V1 just equals R1 times all that. So that becomes your answer. So it's R1 times V, which is the V total over R1 plus R2, that's V1. So this is how you get this, called voltage divider rule. It divides the voltage between R1 and R2, keeping the current the same. So it's easy to guess what V2 would be. V2 would be R2 over R1 plus R2 times V. So you divide the voltage across, the voltage drops across R1 and R2. So you deduce that formula by knowing that the currents are the same for series connection for resistors. If they were in parallel, then the voltage are the same and the current is different. So now you have to use V equals IR voltage Ohm's law to now find the voltage, the current for each resistor. But that is not the case here. Here we're just looking for the voltage across R1. Okay. The next problem says, focus on concept question 09. Two identical resistors are connected first in series and second in parallel. The equivalent resistances of the two types of connections are respectively R series and R parallel. What is the ratio of R series over R parallel? So they're identical. So for series, we know we add algebraic summation R1 plus R2. So since they're identical, it's just R plus R, in this case, 2R. For parallel, is 1 over R1 plus 1 over R2 equals 1 over R total in parallel. But I'm going to give you when you have two resistors in parallel, the easiest way to get the equivalent, instead of doing the one all over, is to do their sum, their product divided by their sum. Their product divided by their sum. If they are only two, if they are more than two, then you have to do two at a time. It's a longer process. But you have to do their product divided by their sum. So in this case, I can just guess the product, since they are the same. Oh, 1 second. Just need to sign for a package. Thank you. Sorry about that, guys. I'm back. Okay. So let me do it the traditional way first. 1 over R1 plus 1 over R2. So R parallel, the total becomes 1 over R1 plus 1 over R2, the inverse. That's what this to the power minus 1 means. It means 1 all over all that. So since they're identical, it's 1 over R plus 1 over R. The LCM is R squared. If you multiply them, R plus R over R squared, 2R over R squared is just 2 over R. So if you take the inverse, it's R over 2 now. So what I'm saying is, instead of going through this long process, since you're looking for 2, it's just R times R over R plus R. So R times R is R squared, R plus R is 2R. So I have R squared over 2R, R over 2. I get it directly. So that's one quick way. We're going to use it as time goes along to make things easier instead of going through this long process. Product divide by sum, if they are only 2. So, but this is the traditional way. So we've summed the parallel ones to get R over 2. The series one gives us 2R. So R series divided by R parallel is 2R divided by R over 2. So this 2 comes up, becomes 4R over R, just number 4 is the correct answer right there. Okay. Now the next problem is focus on concept question 11. It says in the circuit shown in the drawing, each resistor has a resistance R equals 640 ohms. What is the current I delivered by the battery? So these are identical. So these two are in parallel. So I do the product divided by the sum, R squared over 2R. R squared over 2R for this one too. So The R parallel 1 for this first one in parallel is R squared over 2R. It's the same for R parallel 2 for these ones in parallel. So I call this R parallel 1, I call this R parallel 2, and then both of them are in series. So the total resistance becomes R parallel 1 plus R parallel 2 for series connection. So product over sum, that's how I got this equivalent without having to worry about 1 over or anything. So it becomes R squared over 2R plus R squared over 2R, which is what we got before. R squared over 2R is just R over 2 plus R over 2, so which is 2R over 2, you just get R right there. So the equivalent resistance here is R. So the equivalent current is voltage divided by equivalent resistance, 9 over equivalent resistance is just R, which is 640. And you just get your equivalent current from right there. Okay. Now we go to focus on concept question 12. It says in the following 3 arrangements, each resistor has the same resistance R. Rank the equivalent resistances of the arrangement in descending order, largest first. So this one we can easily do. You can do product divided by sum for these first 2, and then the result do another product divided by sum, but it will be too long. So I'll do the traditional way for you to understand, for those of you that are still trying to understand product divided by sum for 2 parallel resistors. So the total resistance here for these resistors is 1 over R plus 1 over R plus 1 over 2R, because these two together are in series. So I do that with to the power minus 1. Don't forget to the power minus 1. If you don't want to put to the power minus 1, then don't forget to put 1 over R total here. So now when I work this, is LCM is 2R. I have 2 plus 2 plus 1 to the power minus 1. So it's 2R over 5, because it's 5 over 2R. The inverse is 2R over 5. So 0.4R. So this is 0.4R. So let's do this other one. So this one is 2R in parallel. So I can just say 2R times 2R over 2R plus 2R. I'll get the answer directly. Or I do 1 over 2R plus 1 over 2R, the traditional way to the power minus 1. I will get the same answer when I take the LCM 2R, 1 plus 1, 2 over 2R, 2R over 2, takes out the minus 1, then 2R becomes, here just becomes R, sorry. R becomes your answer here. Okay. So now for C, I have 3R in parallel with R. So my answer will be 3R times R over 3R plus R. Easy. But we'll do the traditional way, 1 over R plus 1 over 3R. So you're going to get 3 plus 1 over 3R to the power minus 1. So it's just 3R over 4. So your answer becomes 0.75R. So the largest one is B, R, followed by C, 0.75R, followed by A, 0.4R. So that's the correct answer here, with the largest first in the equivalent resistance, followed by the next one. Okay, let's go to the next question. Chapter 20, problem 50. A coffee maker 13 ohm and a toaster 19 ohm are connected in parallel to the same 120 volt outlet in the kitchen. How much total power is supplied? So power is V squared over R. So, but you need to get R because they're in parallel. So you have to sum the R's together. 1 over R coffee maker plus 1 over R toaster. So the product divided by the sum, if you like, or you just put it the way it is, like this, for 1 over R parallel. So 1 over R parallel is 1 over R coffee maker plus 1 over R toaster. So power is V squared over R total. So which is V squared times 1 over R total. And we already have 1 over R total as 1 over R coffee maker plus 1 over R toaster. So I just put this in here. And then I solve for V given for 120, and I put R coffee maker and R toaster, and I get my answer for power in watts. Okay. The next problem, chapter 20, problem 52, goal says the drawing shows 3 different resistors in 2 different circuits. The battery has a voltage of V24 volts, and the resistors have resistance R1 50 ohms, R2 25 ohms, and R3 10 ohms. Determine the current through the voltage across each resistor. So this one is the one that is in series. We're going to come to the next one to see the one in parallel. So this is the A part of the problem. So since they are in series, my R total in series is just R1 plus R2 plus R3, 50 plus 25 plus 10, gives me 85. And then the current through each resistor is the same. So it's my total current. I1 is I2, I3, which is the total current, which is voltage over total resistance. Voltage is 24 volts, total resistance I just got as 85. So I get my total current. Now, the current is the only thing that's the same for these guys. The voltage is different. So what is V1? Voltage across 1 is I, the current I just got, times R1 to give me the voltage drop across R1. For V2, I times R2, for V3, I times R3. So I got the different voltages for each resistors. If I sum them up, it will give me back my 24 total voltage. That's how this works. Okay. That's how you solve the A part. Let's go to the B part when they're in parallel. So in parallel now, they have the same voltages, V1, V2, V3, the same as 24 volts, but the currents are different. So how do I get current 1 is total voltage over R1, current 2, total voltage over R2, current 3, total voltage over R3, just same Ohm's law that we use. So this is how you get different voltages for series connection and different currents for parallel connection through different circuit elements. So we come here, find the equivalent resistance, chapter 20, problem 67, go between 2 points A and B in the drawing. So we want to sum all this resistance. So now I'm going to use product over sum for 2. So let me tell you how I do it. So I start with these guys. 20 plus 10 is in series, that's 30. 30 is in parallel with 60. So I'm going to do 30 and 60 in parallel. It will be 30 times 60 over 30 plus 60. That's the sum of all this right here. And then I add it in series to 35. That's all. I've solved the problem in one line. So these two sum together are in parallel with 60. So these two sum together is 30. 30 is in parallel with 60. So the equivalent here in parallel is 30 times 60 over 30 plus 60. Then that result is in series with 35. So if I do 30 times 60 over 30 plus 60, it's 1800 over 90 plus 35 is 20 plus 35. I just get 55 ohms directly. So you can still do the traditional way, this plus this, 1 over this plus 1 over that. If that is easier for you to comprehend, you get the same result. Just use this result to check if what you're doing is right or wrong. Next problem, that is problem chapter 20, problem 76 says a battery has an internal resistance of 0.035 ohms and an EMF of 9 volts. What is the maximum current that can be drawn from the battery without the terminal voltage dropping below 8.63 volts? So let me explain what internal resistance is. So internal resistance is the resistance inside the battery itself. So it takes some of the voltage before having a terminal voltage. Terminal voltage is the final voltage that comes out of the battery for other things to use. So if your terminal voltage is 8.63, and normally what is written on the battery is 9 volts. So it means that this internal resistance is sucking from this 9 volt how much? So voltage drop across internal resistance is 9 minus the terminal voltage, 8.63. So 0.37 volts is what the internal resistance is taking out. So from Ohm's law, using these volts and the internal resistance, we can get the current in the circuit. So voltage across internal resistance over internal resistance gives you the current flowing through that. And that current is going to be the same because it's like a series connection in this case. Okay. Next, chapter 20, problem 79 says, consider the circuit in the drawing. Determine A, the magnitude of the current in the circuit, and B, the magnitude of the voltage between the points labeled A and B. So this is Kirchhoff's loop rule. So we assume that the current is directed clockwise, and then we are also going our loop clockwise. So we're going in the same direction as the current. If you are going in opposite direction as the current, the whole thing will change. So let me tell you how Kirchhoff's loop rule works. So I assume current is going clockwise. I am also going clockwise. If I do that, I start from anywhere. So I'm starting from the top left corner, which is easier. So anything that passes through any resistor becomes negative. Its voltage drops. And then for cells like batteries like this, I check from where it's coming, from minus to plus. So this is a potential rise, not potential drop. So potential rise. That one doesn't matter the direction I choose for my loop or for my current. So potential rise, and here I'm going potential drop. So it just follows the loop direction only. So I'm going from minus to plus, that's potential rise. So I'm going from minus to plus, so it's going to be plus 30. I'm going from plus to minus, so it's going to be minus 10. But it's going to be minus I times all of these other guys because the direction of the loop is the same as the direction of my current. So I'm going to have minus 5I plus 30 minus 27I minus 10 minus 12I minus 8I equals 0. So this is sum of potential rise and potential drop equals 0. So if you rearrange, 30 equals all that. So you can say potential rise equals all the potential drops. This is another way to write the expression of Kirchhoff's loop law, if you like. But I like to use this minuses for the resistance and pluses for potential rise along the voltage cells and minus for potential drops across the voltage cells. So if I had taken my loop direction to be opposite my current direction, then everything would change. So let's say current is going clockwise, I'm going counterclockwise. So all these minuses will become plus 5i, plus 27i, plus 12i, plus 8i. And since I'm going counterclockwise, so this, instead of coming clockwise, was from plus to minus, now it's from minus to plus. So this is going to be plus 10, and this is going to be minus 30. You're going to get exactly the same answer. So it doesn't matter the direction of current and loop you choose, just follow the correct sign convention. If the direction of current and loop are the same, when they pass through a current circuit element like a resistor, is going to be a voltage or potential drop. It's going to be negative I times the resistance, negative I times resistance. And if you come across a cell, see from which terminal are you going to which terminal. Are you going from a positive to negative? It's going to be potential drop. Are you going from a negative to positive? It's going to be potential rise, so positive. So you take the last terminal you pass through, the sign on the last terminal to be your sign. So in this case, I choose, so I'll go over this again. I choose my circuit, my current clockwise, my loop clockwise, the same. So I'm going to have negative 5i, and my loop is coming like this from minus to plus, so plus 30, minus 27i, plus to minus, minus 10, minus 12i, minus 8i equals 0. And then here I solve. 30 equals, sum these up, all the i's. So 30 minus 10 is 20 equals 52i. So I is 20 over 52, and you just get that answer for the A part. So for the B part, is asking for the magnitude of the voltage between points A and B alone. So for points A and B alone, following the same direction, I have plus 30 minus 27i. That's all I have between points A and B, nothing else. So plus 30 minus 27i, and I've already gotten my I. So 30 minus 27 times that I gives me the voltage across A and B, and 19.62 volts. Okay, that solves the problem for chapter 20, problem 79. So let me go to the next one. Chapter 20, problem 82, go. So using Kirchhoff's loop rule, find the value of the current I in part C of the drawing where R is 7 ohms. So this is the part C. So this is the drawing. So we're going to use the same thing. Start from the top left, take our current to be flowing that way clockwise, take our loop to be also clockwise. So this is going to be plus 36 from minus to plus, so plus 36 minus 3i minus 12, because it's from plus to minus. So minus 12 minus 4i. So all these are going to be minus all the time, so long as my loop direction is the same as my current direction. If I choose my loop direction and current direction opposites for some reason, if I have maybe multiple loops, is that okay? Then I have to put plus instead of minus for these guys. That's the only case. So I'm going to have 36 minus 3i minus 12 minus 4i minus ri, which is r is 7 minus 7i equals 0. So here I just solve 36 minus 12 equals all these guys sum together. 14i equals 24, I is 24 over 14, 1.714 amperes directly. So this is how you use Kirchhoff's loop rule to solve problems, basically. Okay, chapter 20, problem 95. 3 capacitors are connected in series. The equivalent capacitance of this combination is 2.5 microfarad. 2 of the identical or individual capacitances are 6.3 microfarads and 9.9 microfarad. What is the third capacitance? So they are in series. So if you're in series for capacitors, it is like resistors in parallel. So capacitors and resistors are skewed. You sum parallel capacitors the way you sum series resistors. And you sum series capacitors the way you sum parallel resistors. So parallel resistors, it's 1 all over, 1 all over, 1 all over. That is how we sum series capacitors. So the total capacitors in series is 1 all over capacitance in series, 1 over C1 plus 1 over C2 plus 1 over C3. So we are given the total, C total. We are asked to find C3. So 1 over C3 is 1 over C total minus 1 over C1 minus 1 over C2. C total is given 2.5. So I put that in here. Minus that, 1 all over all the results gives me C3. Don't forget the power minus 1 to get C3. So that's what's happening here. So 1 over C3 is this, then C3 becomes 1 over all of this. And then I put C total to be 2.5, C1 to be 6.3, C2 to be 9.9. And I solve this out and I get my answer carefully. So this is how you work this problem. So that was chapter 20, problem 95. Now let me go to chapter 20, problem 96. It says 2 capacitors are connected to a battery. The battery voltage is V equals 90 volts. And the capacitances are C1 equals 2 microfarad and C2 equals 4 microfarads. Determine the total energy stored by the two capacitors when they are wired in parallel and in series. So in parallel, they are like resistors in series, we sum them. So when they are in parallel, the normal formula for energy stored in a capacitor is half CV squared. Half times capacitance times voltage squared. So the capacitance is the problem. So that capacitance, there are two of them. When they're in parallel, I sum them. So that's what gives half C1 plus C2 V squared when they're in parallel. But when they're in series, I have to get the product over the sum. If you like, 1 over C1 plus 1 over C2 equals 1 over C equivalent. So I have to find this capacitance total first before I put it as half times CV squared. So half times CV squared for parallel, I sum the C1 and C2, I get my answer. Half times CV squared, but for series, to get this C, I get 1 over C1 plus 1 over C2 inverse. And that's how I get this guy. So these are the two different answers. It's half times CV squared, but the C for parallel is the sum of the individual C's. You get the first answer. Half times CV squared for the second answer for the B part, but the C for series is by solving this inverse 1 over C1, 1 over C2, and then take inverse of your answer again. So whenever you add these two together, you take inverse of this result to get this one. Then that is what you put as half CV squared for the series connection. That's how you get these two different answers right here. Now, chapter 20, problem 97 says, determine the equivalent capacitance between A and B for the group of capacitors in the drawing. So between A and B, all these capacitors. So they started from here, 24, 12, and 8 are in series. So it's going to be 1 over 24 plus 1 over 12 plus 1 over 8. I get that in series. So 1 over my answer, 4 microfarads. So 24, 12, and 8 gives me 4. Don't forget, series capacitance behaves like resistance in parallel. Now, these 3 are in parallel with these 4. Remember how to know if something is in parallel? When you break the circuit, it can pass through another branch. If I break the circuit here, it can pass through here. If I break the circuit here, it can pass through here. So I know these 2 branches are in parallel. But all these are in series because if I break the circuit, nothing can get here, nothing can get here at all. Okay. So these 3 are in series. I sum them up. I get 4. 4 is in parallel with this other 4. So I sum those two together, 4 plus 4 for parallel, 8. So all these give me 8. Now that 8 is in series with 5 and 6. So I have 1 over 5, 1 over 6, 1 over 8. I get another equivalent capacitance, which is my total capacitance for everything, to be 2 microfarads in this case. Don't forget, when you sum all this, you take 1 over to get C. That solves that. And then the last problem says, a circuit contains a resistor in series with a capacitor. The series combination being connected across the terminals of a battery. The time constant for charging the capacitor is 5.1 seconds. When the resistor has a resistance of that, what would the time constant be if the resistance had a value of that? So you're given different resistance and different time constant. So time constant is just resistance times capacitance. So time constant for A is resistance of A times capacitance, and time constant B is resistance B times capacitance. These resistors are what is changed here. The capacitance is kept constant. So when I divide tau A by tau B or tau B by tau A, I will get RBC over RAC, is just RB over RA. So tau B is tau A times RB over RA, and I have everything. I have tau A, I have RB, I have RA. So I'll get the time constant for B from here. And that solves this problem for us. And this is the end of homework 20B. I'll see you guys next week. Have a good one.